Next up is Dr. Lisa DeVetter. She is the small fruit horticulturist for Washington State University. She'll be talking about managing soil-borne diseases through removal of root inoculum and red raspberry.
All right, can everyone hear me all right? Little light, okay. About this. Well, first, thank you, Sean, for that nice introduction, and thank you to Duncan for the nice segue into this presentation's topic, as well as giving me a little extra time to talk. That can be nice in some situations. So today my goal is to introduce a project that was started in 2014, and the project is looking at this whole idea of what effect removal of raspberry root and crown inoculum has as a pre-plant management technique in red raspberry. Now, before I begin any further discussion, I want to make sure that I acknowledge the collaborators in this project and other investigators, Dr. Zazada, as well as Dr. Jerry Weiland, and of course, Dr. Walters. And then there's there's Rachel Rudolph, who you heard earlier this session, who did the clicker survey, Sean Watkinson, the technician in my program, Mark Mazzola, who hasn't been directly involved yet in this root removal project, but is helping us answer questions about soil microbial ecology and how it changes as a result of different management practices. And lastly, Suzette Galinato. She's an economist in Pullman with Washington State University. And of course, I want to acknowledge our grower collaborators, our grower cooperators. I really consider them really collaborators. They've been immensely helpful in this research. So just going to go through a little bit of an introduction and build the rationale about why we're interested in soil-borne disease management practices in red raspberry. So the red raspberry industry here in Washington is vibrant. You are probably really all well aware of that. We're the largest producer of processed red raspberry, and over 90% of that production comes here in Whatcom County. And it's very valuable, close to $61 million in 2014. And depending on the year, it's really staggering. But if you look at it at a national level, Washington is responsible from 59 to 88% of total U.S. raspberry acreage. But despite the success of the industry, there are challenges, and soil-borne disease management is one of those challenges. Fields that used to remain in production for 15, 20 years are now being removed, renovated, and replanted on that same ground every 5 to 8 years. And there's many reasons for this, and I'll discuss that a little bit more later on. But you know, we're replanting because this land suitable for production is limited in red raspberry, and soils are typically fumigated prior to planting. Fumigation occurs in the fall or in the spring occasionally, and they're typically applied by commercial applicators. Now that's changing a little bit with Bidate and growers purchasing their own rigs to apply this product, but traditionally had been provided by commercial applicators. Most of the fumigators like Telone, C35 are deep shanked and injected in the soil at a deep depth, anywhere from 12 to 18 inches, and they're left untarped, which is an important factor to note because if we tarped, we might see better control. Some of the primary fumigant products that the industry or that we are using are Telone C35 and then Bapam, which is metam sodium. Despite fumigation, we're still having issues with managing soil-borne diseases, and this picture from Skagit County represents that to some degree. So this field was fumigated, but it was overcome with Phytophthora rubi, and we verified that Phytophthora rubi was the causal agent causing decline in this field. And again, the reasons for this are many. One is changes in land management. We're seeing a decline in rotation, like with potatoes and wheats and pasture for dairy. We've also had the loss of some of our traditional soil fumigants, methyl bromide being one of them. There's also increasing restrictions on fumigant usage. The re-registration eligibility decisions exemplify that. And really, there's been a lot of questions about this need to optimize our fumigation practices. In some situations, and Rachel highlighted this to some extent, there's concerns about soil quality, especially soil biology, and how microbial populations might be affected by fumigation, and how this all might contribute to this phenomenon that has been described as replant disease, where we see decline in productivity and longevity of a planting, when raspberries replanted into the same ground. But we really don't have a good understanding of, what are all of the factors in red raspberry that contributes to replant disease. Want to highlight, I know we've talked about this before, but the two known soil pathogens that we do know to contribute to soil-borne disease and replant are Phytophthora rubi, or Phytophthora root rot, and Pratylanchus penetrans, which is root lesion nematode. Phytophthora root rot, it's a water mold, and its reproductive structures, the oospores and the mycelia, can persist in the soil for many years. I've read for at least Phytophthora figarii up to 14 years. And the infection can damage the root system, which can have some pretty devastating effects on the plant that we typically start to see with the onset of high temperatures and fruit production. Root lesion nematode has a very broad host range. I've read up to 200, but I don't know how well characterized that has been. And high populations of this organism can cause root dieback, stunting, and it can behave synergistically and worsen disease symptoms if it's in combination with other diseases like Phytophthora root rot. And both of these organisms are present here in Whatcom County raspberry. So the small fruit horticulture program, which I lead, has invested a lot of effort into looking at improved soil-borne disease management in red raspberry. And our goal is to develop improved horticultural tools for soil-borne disease management. We're really fortunate to have an opportunity to work with a lot of other scientists and excellent grower cooperators in addressing these questions. The co-investigators are good examples of that. We're really taking a diverse approach, though. We're looking at alternative fumigants, such as Dominus, or methods of fumigation, like tarping, different application depths. We're looking at the application and management of cover crops to see if cover crops, if they're a bridge, how can we manage them to reduce the potential carryover of soil-borne diseases, primarily root lesion nematode. We're also interested in understanding more about soil ecology and how it contributes to replant. And then lastly, we're looking at root and crown inoculum. And this is what I'll be spending the remainder of my time focusing on. So a lot of you might be asking, why root and crown inoculum removal? Again, Duncan provided a nice segue into this. What we've observed is that there's large amounts of root and crown material that remain in a field prior to fumigation. And this material could serve as a source of inoculum for the next planting. A lot of the fumigants are unable to penetrate large tissue. So that, again, further leads us to consider this material to be a source of inoculum because the fumigant can't necessarily penetrate that. This image here is a field in Whatcom from one of our grower cooperators, and I think it demonstrates pretty nicely in the single row that's part of our experiment the amount of root and crown inoculum that remains in the field. Now this would be essentially chopped up and incorporated in the field prior to fumigation. But even those larger pieces that can serve as sources of inoculum, or we suspect can serve as a source of inoculum. So the overall goals of the root removal project are twofold. Short term, we want to evaluate and demonstrate the potential efficacy root inoculum can have as a pre-plant management technique in red raspberry. And long term, this plays into an overall larger goal of the program and many other scientists working in this area, and that's to develop practical and improved tools for soil-borne disease management and red raspberry. Now, for the root removal experiment, there's two experiments. For the first experiment, we're looking at the efficacy of root removal and looking at different possible devices that can be utilized to implement root removal in a field. So for this experiment, we compared 3 different root removal devices, and we looked at the speed of these devices and their efficacy in removing raspberry roots. Again, this is a nice moment to acknowledge Ms. Suzette Galinato. She is doing the economic piece of this, and really is an important part to help us understand if we're going to be looking at this as a technique, what are the economic costs and what are the potential economic benefits? The devices that we tested include a Lundeby plant lifter, a beach cleaner, and a potato harvester. And there's images of these devices here on this slide, the top being the Lundeby plant lifter and the lower right, the potato harvester. These are locally available here in Whatcom County. The beach cleaner is also locally available, but it's not a common implement. This was something that one of our grower cooperators purchased on his own devices to remove root material in his own field because he thought it was contributing to soil-borne diseases. And so we were able to cooperate with him and collect some data for this experiment. So here are the results for experiment 1. Here on this table, we have the different devices, the speed in the central column, and then on the furthest right column, the percent of root and crown material removed. So you can see that the slowest device at a quarter mile of an hour was the Lundeby plant lifter, but it also was the most effective. It removed 98% of the root and crown material. The fastest was the potato harvester, and that removed about 96% of the root and crown material. And then the least effective in terms of removing the root material was the beach cleaner, and it had a moderate speed at 0.37 miles per hour. Now this image here just shows the amount of material that we removed from a 2 by 2 by 2 foot or 4 cubic foot area of soil. On the right, you have the amount of roots that remain in that area, and on the left, what you see are the roots that have been removed from a Lundeby plant lifter. So in experiment 2, we wanted to look a little bit more closely at the effects root removal has on soil-borne population or soil-borne disease populations. This experiment just started in August of 2014 in a field that was originally planted with Schimanus and has been replanted to Meeker, and this was a field site located here in Whatcom County. So the overall objectives was to look at the effects of root removal on soil-borne diseases. Specifically, we were looking at Fusarium and Pythium because this field did not have root rot or Phytophthora pressure, so we utilized those organisms as proxies, and root lesion nematode. And we also wanted to look at how the raspberry plant responds. So we're looking at plant growth, plant development, and this coming year, yield. So the experimental design, I'll just go through this real quickly. We had our main plots were fumigation with Telone C35. We worked with Trident Agricultural Products to apply the product. And then the split plot was the root removal. So we had every combination, fumigation, no fumigation, root removal, no root removal, and that was replicated 6 times in our commercial field. Now the main plots were 100 by 30 feet, so they spanned 3 rows, and we collected our data from the center rows just to minimize any potential buffer effects from the application of our treatments. And as I mentioned, the data that we collected included changes in soil-borne disease populations, Fusarium and Pythium, because again, we didn't have Phytophthora rubi in that field, and root lesion nematode, and then we're monitoring plant growth and yield. So here are some of the preliminary results. Now these are Pretolanchus penetrans or root lesion nematode populations and how they change over time. I want to give credit to Dr. DeZada. We collect the roots and we send to her, and her lab is instrumental in extracting them and helping us generate these data. So on the y-axis, we have Pretolanchus penetrans per gram of root. And on our x-axis, we have month in 2015. And then the bars, the different colors, just to guide you. So in dark blue, we have fumigation with roots. This is standard industry practice as of present. The light blue is fumigation with roots removed. The dark red is non-fumigated with roots. And then the lighter, it's a pinker color, but it's looking maybe a little peach, is non-fumigation with roots removed. So what I want to highlight here is that March, April, May, we really don't see any changes in populations of root lesion nematode. In June, although you can't really see it given the scale, we start seeing differences, and we see a fumigation effect. Fumigated plots, whether or not they had root removal, had lower populations of root lesion nematode than non-fumigated plots. However, when we start moving into July, August, September, and October, that difference is lost. So the non-fumigated plots have the same number statistically as the fumigated plots. So we're basically by August back to pre-plant root lesion nematode levels. So 1 year after fumigating, we're back to our original levels prior to fumigating. So on this next slide, we're looking at changes in Pythium soil populations, papricles per grams of root. And here I'd like to, you can't really see it, but this figure is courtesy of Dr. Jerry Weiland, who, again, we help collect the roots, and Dr. Weiland's lab has the tools to extract these organisms and look at them. So what I want to highlight here, and these data are similar for Fusarium, is that pre-treatment, so prior to root removal, prior to fumigation in August, all of our plots are statistically the same, and that's important. So we don't have any differences prior to implementing our treatments. By November of 2014, so 6 weeks after treatment, we see a fumigation effect. Non-fumigated plots have higher populations of Pythium than non-fumigated plots. However, by pre-plant time, so February of 2015, we've lost that benefit. So we're essentially statistically the same. You can see some numeric differences where the fumigated plots have less Pythium, but at the statistical level, we're not seeing a difference pre-plant. And on this next slide, again, courtesy of Dr. Weiland and his lab, we're looking at percent colonization of root debris by Fusarium. The data are similar for Pythium. And we have our time points again. So our time points being pre-treatment, prior to implementing our treatments, where our populations of Fusarium are the same. And then we have 6 weeks post-treatment. And again, they're the same. And pre-plant, they're the same again. So what we're seeing here, and these are just from our plots with roots, because it wouldn't make sense to look at these numbers from our root removal fields, we shouldn't have roots, is that even if we fumigate, these larger pieces of root and these debris are still reservoirs for Fusarium and Pythium, even if we fumigate. So we looked at some plant metrics, and we looked at mean number or average number of canes per hill in these plots, and then the average cane height from these plots. And these figures are condensed because really there's nothing significant statistically that we're seeing, which is really interesting. Even though we're seeing these differences in Pythium, Fusarium, and root lesion nematode populations, we're not seeing a response yet in the plants. The cane number per hill is the same, and the height of the canes are the same. So what are the next steps for this project? Well, we're going to continue monitoring it. We're going to be heading out to the field here again in December and collect monthly root lesion nematode data. So any volunteers, wet and muddy out there, we'll always take them. We're also going to be collecting our first set of yield data, which will be really interesting to see how yield is affected, if at all, by these various treatments. And we're also repeating this experiment in another field site, which does have Phytophthora rubi present in the field. So we'll be able to see if this treatment has any effect on that particular organism. Another side project that emerged from this project related to what we do with all of the root and crown material that is generated through the process of root removal, because a large amount of material is generated. So the question that we asked ourselves is composting a viable option for removing and getting rid of this root and crown material? Can we create a valuable product? So we worked with a local composting facility here in Linden, Smith's Compost, and they composted the material removed from our field experiment. And what we did once the composting process was complete is we collected that material, and we are finishing up a bioassay where we grew tissue culture meeker plants with and without compost that had root material in it. So essentially we looked at tissue culture meeker with the compost that had the roots in it, and then the regular compost that this composting facility produced. We also removed pieces of the roots that still remain in that compost, and Dr. Weiland looked at the presence of Pythium and Fusarium. So what we found in our first round of this greenhouse assay, we just repeated the second one, is that Pratylenchus penetrans was reduced to non-detectable levels through composting. Fusarium and Pythium, likewise, we found undetectable levels in our composted root material. Again, big question though is it's quite an endeavor to take that root and crown material and haul it to a composting facility. So a big question we have is, okay, we've demonstrated that this material, composting is effective at removing the pathogens, but is it economically viable for a grower to do this? And Ms. Gallinato will be helping us address that. So some thoughts moving forward. The first point that I want to mention is that conventional fumigation is leading us to have some unsatisfactory results. We're seeing pre-treatment levels of some of our target organisms not even 1 year after the treatment. So I wouldn't go and not fumigate my fields by any means at this point if you have these organisms in your fields. But it's pointing to the fact that we have an opportunity to optimize our fumigation practices to get better control of these organisms affecting our production. Dr. Walters already addressed this, but there's some concern that we have about the role cover crops might play. Now, cover crops are valuable in helping build our soil, and they're typically planted after they're typically grown after fumigation. So there's a cover crop after fumigation and prior to replanting raspberry. But we've seen some very high numbers of root lesion nematode in that cover crop. So are cover crops a bridge? That's a question we would like to get a definitive answer to. Are there ways we can manage the cover crops, whether it be timing of planting or method of cover crop destruction, like application of a systemic insecticide like Lanate, that would reduce nematode populations and reduce that chance of the cover crop serving as a bridge? We've also, Dr. Walters has generated some really interesting data about the efficacy of Dominus, the allele isothiocyanate, the mustard horseradish product, and metam-sodium orvidate. And so we started trials with those particular products. And we have a joint grant through the Washington State Department of Agriculture Specialty Crop Block Grant Program that is helping us address some of these timely questions and concerns. So as I close, I again want to acknowledge my collaborators and my co-investigators. I also want to acknowledge Sean, as well as Chris Benedict with Whatcom County Extension, and Rachel Rudolph, who's the graduate student, as well as Rachel Weber and Jack Pinkerton that helped with various aspects of the project. A big thanks to our grower cooperators. I'm internally grateful, and that's John Mayberry with Mayberry Packing and Randy Honcoop with Honcoop Farms, and also want to mention Larry Tremaine, who we're working with for the other root removal project, as well as Schmidt's Compost. They were the company that received the compost and helped us run this trial. Tim Purcell with Trident Agricultural Products. He's been immensely helpful and supportive of our research and all of our, experimental design requests that are maybe potentially cumbersome for him. He's been very gracious about it. The Whatcom Farmers Co-op, and then the Northwest Center for Small Fruits Research, which funded the first experiment that I spent the most time discussing, and then the USDA, which is funding the second project where we're looking more closely at root removal and its effects on Phytophthora. So with that, I'd like to thank you all for your attention. I believe I left some time for questions. And I ask if there's any questions, and Daryl's not here. So I think someone else has to pick up the baton and get the ball rolling with questions.
That's perfect then. I can be first. I noticed a lot of the research, especially the fumigation, is in reducing numbers of these organisms. Mm-hmm. Is there any research, I think you touched on it, that you're working with someone who's looking at soil ecology, ways to bolster like a probiotic effect, maybe organisms that compete with those or that will reduce the numbers, so compost applications, synthetic fertilizer applications. Is there any future research you're planning on doing?
Yeah, well, so let me repeat just to make sure I understood the question correctly. So the question, are there any research projects underway that are looking at some more biological approaches that would help reduce soil-borne pathogens by building up beneficial microorganisms or post-fumigation? And I'd say, it's an emerging field right now. And yes, there are some things that we're starting to look at within my own program. And there's others that people have looked at as well in other cropping systems. One being brassicaceous seed meal. It's a byproduct of canola oil extraction. And what we've seen in apple is that addition of brassicaceous seed meal has had positive effects on soil microbial ecology and creating essentially a soil that's suppressive to diseases. And those can have pretty long-term effects. And that's been seen in apple, and we're starting to see that with brassicaceous seed meals and anaerobic soil disinfestation in strawberry. We haven't looked at this closely in raspberry, but we're starting to. A big question that I have, though, about brassicaceous seed meal is, if if this is an option, how widely would it be adopted? Because the costs are quite high, and that's where the economics help come into play. It can help us assess the effectiveness of this treatment from a management perspective, but also help us look at it as from a cost perspective, because that's a major driver for practices. Yep. Thank you. Okay. Well.
Any more questions?
Okay.
All right. Well, I guess that's it.
Thank you.
Thank you, Lisa.